Thanks for coming. I'm super happy to talk about this because I've been doing Rust at Sentry for a long time now, and I have been introducing this language at Sentry. And so we have 7 years of experience of building stuff with it in a commercial context, which is really nice. Since we mentioned karaoke before, Sentry's early days, so we were a small little company, and now we are like 400 people. And so we went from one person doing Rust to more engineers doing Rust. And so it makes me very happy. And what does that have to do with karaoke? Because if you're familiar with Sentry, very early Sentry days, David Kramer, our founder, used to sponsor karaoke nights. So that's the connection. So who am I? My name is Armin Ronacher, and I do open source for many years. Originally Python. I wrote quite a few libraries in Python or contributed to them, including the Flask framework. And I just really like open source. I had some period of time in my life where I worked for a computer gaming company, but in the last 9 years, which is for how long I'm doing Sentry now, I'm very glad that I can do open source, because Sentry, I would say, by my definition, is open source, but we'll go into this a little bit. So what is Sentry? Sentry is, or when we started, was an error monitoring company. So you can load our SDK into your code, and then when it encounters an error, it will log that. And with that comes a bunch of processing that we need to do. Nowadays, we do a bit more. So there's some distributed tracing going on. There's some session replay stuff going on. And it's a 100% source available. It's 95% open source. And the reason for this is that we write a lot of our software right straight under BSD or Apache 2, but some of it is under the BUSL, which is a license that for 3 years comes with the restriction that you cannot operate a competing service with it. You can run it yourself as much as you want. And because we don't write that much code every year, most of the stuff that is BSL licensed has already flipped over and is now fully Apache licensed. And we were, and still are, a Python shop. So a lot of the code that we have written is Python. So that's sort of the history that you should know, because the fact that there is a lot of Python really plays quite a bit of a role in this. So I'll not bore you too much with the user experience of the product, but in terms of the talk, it's good to understand what it does. It might be hard to see what this is, but this is a stack trace from a TypeScript application. So you mentioned there's an SDK. It encounters an error, so it gets the stack trace, and it sends a stack trace to us. And what's the problem with this? Well, the problem with this is that JavaScript is minified, bundled, transpiled. So you don't actually ever see a TypeScript error. You usually see a JavaScript error. And so first part where Rust comes into play is that we have to apply source maps. So we take the minified stack trace, and then a bunch of Rust code runs that converts that into the original stack trace that you would expect as a TypeScript programmer. We also have replays. Replays are what you kind of do on the internet in your web space. So if you're on a website that's instrumented with Sentry replays, there's a little script in there that captures the DOM. There's some stuff that's happening on the client SDK, but there's also an ingestion system written in Rust that removes any PII that might still be left there by the SDK. Again, all of this goes through Rust. Profiles is one of the 2 areas where we do debug information file processing. So a profile is, there's a sampling profiler going on in the SDK that captures every couple of milliseconds what's happening on your stack. And for all of those, they're just memory addresses, right? And so what we need to do on the server side, again, all written in Rust, is taking those memory addresses, finding their corresponding debug information files, and then converting every memory address into a human-readable function name. Traces are not that interesting, I think, but we send them through a system called Relay, which client sends all of the traces, and then for a very small percentage, let's say 1%, we retain them. And so the logic for if we want to retain them or if we want to throw them away is, again, in Relay, which is a Rust component. And then if it wants to throw something away, it keeps metrics and sends that on to the rest of the system. So why Rust? So when I started working at Sentry, it was all Python. I had some personal interest. We were a very small company. And I have a lot of reasons that I thought at the time were reasonable to introduce Rust to the company. But they're sort of retroactive, right? It's like, this is your toy, you really like the language, you start playing with it, and then find all the arguments why you should be using it in a company. But there were actually some reasonable arguments too, other than personal interest. If you've ever written Python code and you have particularly used someone else's Python code, you will have discovered that packaging in Python is not great. It's not great in 2023, and it wasn't great when we started doing this, which meant that if I want to send a command line executable for someone else to run in CI, it was way better to ship a binary, sort of was mentioned already earlier today on the talk, than to have people install this with pip. And the other thing is that we could actually reuse code in the Python code base with it, because it's actually very nice to write extension modules, even at the time, in Rust. And what's actually quite nice is that the runtime behavior is very predictable, and we'll go into this a little bit. So for a Python company, Rust modules fit quite well. I think that any company's origin story is a legend, which is, I don't remember quite as much anymore of why we came to that conclusion and why it worked out. I think technology choices are not nearly as intentional as we might think nowadays. So as an example, Jane Street is a company that famously uses OCaml. Are they more successful as a result of this? I don't know. I can say for us, Rust was a good choice. We'll do it again. There's maybe an alternative version. We would have written everything in C++. Who knows? To put this in perspective, when we started doing this, there was only Python code and JavaScript code. Nowadays, there's TypeScript code, there's Python code, and there's Rust code. And there's substantially less, but still a meaningful amount of Rust code compared to the Python code. But the Rust code also does quite a bit. And it is, at least by my measurement, the first most popular language by lines of code written. And I also think like every line of code in Rust makes a ton of sense. So I think it's like very information-packed. So why we picked it, I went into this a little bit, but there's sort of the point where you commit to continue doing this. And the commitment to continue doing this is quite a bit more meaningful than the first line that you land initially. So there are many programming languages that sort of popped up and popped down at Sentry, but Rust stuck around. At runtime, this thing behaves quite a bit like Python. So what I mean by this is that Python is a language that has two very important properties that are quite interesting. One is that it does have a garbage collector, but there are companies that use Python without the garbage collector. How do they do it? They rely on reference counting. And I think a lot of production Python code actually mostly gets garbage collected through the reference count and not through the cycle detector. The moment you have an object in Python that has a finalizer, it's actually fully, if you would actually create a cycle, it's uncollectible, and it just leaks. So you write Python code in a way to try to reduce cycles anyways for that reason. And so Rust code fits really well into this. Python doesn't have a JIT, at least modern Python might be getting one, but for many years Python did get JIT, which meant that the runtime behavior that you would get in Python is more or less consistent. It doesn't require that much warm-up. And in both of those cases, Rust fits really well into it because it kind of behaves the same way. Right? There's a lot of there's reference counting going on for memory management if you don't get to determine who the owner is, and you also don't have a crazy runtime that does weird things in the CPU. So you can take a Python service and take a component that's kind of slow and replace it with Rust components. Maybe it's a little bit faster, and nothing really crazy changes in terms of how the server behaves. There is a little bit of memory fragmentation challenges going on. Every once in a while, it looks a little bit weird. You put GM allocator in, maybe it gets a little bit better, maybe it doesn't. But it's not like there's like this thing that we have with the JVM where like you gotta fine-tune the garbage collector and does all kinds of stuff. And it performs really well for a long time. We had some services that we wrote over the years that don't exist anymore that were in Rust that we wrote, they kept operating, and we didn't look at them for a really long time until it wouldn't compile anymore because the dependencies were yanked and stuff. So it's very, very stable and very nice. When we started using Rust for Python extension modules, there was no PyO3. We also had Python 2 still. One of the problems with Python 2 was that it didn't have a stable ABI, which meant that we felt like, I don't know if it's reasonable with the power of hindsight, but it felt like it was a good idea to compile to a shared library that is not linked to libpython itself, and then we have a header file generated, and then we would make a high-level wrapper where we use CFFI to load on the Python side a C library, like a C ABI that is behind-the-scenes Rust, and then use it this way. That allowed us to build a wheel, that's what it's called, that's independent of the Python version. So we could load it on Python 2 and Python 3 at the same time. Nowadays, Python 2 is dead, and also Python 3 has called as a limited stable API, so you can actually build this against any version of Python 3. So you don't need to do any of that nonsense anymore that we did, and can use Python 3 and Maturin instead, which are really, really good. This is incredibly well executed and a really good user experience, and you should be using that instead. So what are the unexpected wins that we got out of this that we didn't expect? I think for me, an interesting one is like the people that are committing to Rust behave different when they commit to Rust than they commit to Python. And one of them is that a lot of the work that we're doing in Rust is outbound. So I give you the alternative version of this. Sentry's core Python monolith has a lot of rendered libraries with a bunch of patches on that never made it anywhere back to the community. Why? Because it's such a pain to depend with Python's packaging infrastructure on a Git fork of a dependency. So it's an extra effort that we have to do to upstream a change. In Rust, I can fork the repository of a crate, and I can commit there, and I can depend on the Git override, and it's really nice, and it's not any effort extra compared to maintaining the fork on our side, which means that quite a lot of the things that we did over the years, we upstream straight to the original crates. And that's because Cargo is so good at doing that it changes the natural thing that we would be doing. So I think Cargo, in a way, forced us to do or encouraged us to do the right thing. And so a lot of the changes that we've built over the years are in external crates like PDB, Gimli, crates like that, rather than in our own crates. It has really well standardized tooling, and I think cannot be overstated how good this is. I can go from one crate to another crate and it looks very familiar. Yes, there are some differences in it, but they are almost universally enforced lints. A lot of crates run Clippy. Even if they don't run Clippy, they run Rust format usually. They're very well-established patterns. Even the base Rust warns you if you do some things that we no longer think are reasonable. And jumping between code bases is very natural. And not just between different Sentry code bases, but also between our own code base and then a third-party crate. And as an example here, I can take code from our Sentry code base, and I can separate it out into a crate that someone else can use, and it doesn't take me a lot of time, or the other way around. In comparison, I wrote the first version of our native crash reporting library in originally C++, and I wanted to take some code in from one of our dependencies called breakpad, which is also written in C++. And it wasn't possible for me to move this code. And in fact, it was easier for me to rewrite this code because that code base had its own string type. It had its own utility functions hidden somewhere that were impossible to move in. And even if I could have moved them in, the code style was completely different. It didn't feel natural in that environment. So it's a very, very different environment compared to C++, which we actually at one point had a decent amount at Sentry at, because we used LLVM, we used breakpad, crashpad, which are all C and C++ libraries. And we have fully abolished any existence, as far as I'm aware, of C++ in our ecosystem other than the client SDKs. So developer experience is really, really good. And I do think that a lot of people use Rust despite the borrow checker and not because of the borrow checker, or despite of safety, because the developer experience is so good, particularly if you come from Python where everything is painful. This is just like, I'm willing to accept a whole bunch of things that seem unnecessary in the first place just to have that good experience, right? As an example here, I want to call out the documentation, actually. So we still have the same developers committing to Python code as Rust code, or at least there's a certain overlap between those two engineering bases at Sentry. And the same person will comment a method in Rust and will not do anything in Python. That's in parts because we actually publish the documentation for internal crates to GitHub, so you can see them there. There's a utility in it. But also because I wouldn't even know how to print, how to generate HTML documentation of Python today. I'm not unaware of a tool that can even do that for our code base. So nobody does, right? It's a completely uncommented blob of Python code. And on the Rust side, someone even made the effort to put the logo into the crate documentation. So that the existence of the tool makes it more obvious for a developer to actually do documentation, and then all of a sudden, you enjoy this also a little bit more. Types and borrow checker, I think this is somewhat obvious. This is why I think advertised, at least we all use Rust. But the types in Rust make sense. They're really helpful. They do a lot of stuff. The types in Python, on the other hand, they are at times very frustrating because they are feeling like an extra thing on top. So the types in Rust really, they're helpful. You can do a lot of really cool stuff with them. Serialization, deserialization kind of fits into the system. And over the years, the board checker went from, well, this is really annoying, to this is actually really helpful. And now I'm looking at Python code makes me deeply, deeply suspicious. From like, I'm passing this object over there, and as a byproduct, this function manipulates it, and then that works because nobody else holds it afterwards. I'm surprised in many ways how stable our Python code base works, which also, to me, implies that perfection is not all that necessary. Our company really requires Python to operate because we can do a lot of things really quickly with it, whereas some things we couldn't quite do in Rust at the same iteration speed. So there's a little bit of maybe over perfection what we do on the Rust side. But it does make us a better programmer. Like if you write Rust code and then you go with all the knowledge of like how to better protect yourself against concurrency issues, or how to better structure APIs so that you're more deliberate about who owns the memory, you also write better Python code. Now we come a little bit into like things that maybe didn't work out so well, so unexpected issues. This is a very weird kind of thing, but out of the box, I think most Rust code is sort of performant. At least it's most likely going to outperform the comparative Python code by quite a bit. But there's certain common or somewhat common things that are actually really slow. One is large error types that I want to call out, and the other one is string clone and friends of that nature. This one is sort of my canonical example because I was impressed how bad this impact is. So I have a Rust implementation of my Python templating engine called MiniGinger, which is an interpreter. It's sort of modeled after the CPython idea of like interpreter loop and bytecode and stuff like this. And so there's a hot loop of where like you switch between every single opcode that you can do, and you run a bunch of operations. And there are function calls that call other things. And I would say like 95% of all the functions in the templating engine return a result of type T and the MiniGinger error type, which originally was just the lowest struct. And then eventually, I kind of forgot how big this struct was going, and I started boxing it, and it went 25% faster, which is a meaningful amount, but there was actually nothing in Clippy that would tell me that my error type is too big. And it's also unexpected that it's such a meaningful difference. And in parts, this is because they do a bunch of things like map error and stuff like this, where the optimizer is maybe not necessarily always able to elide the moves that you would expect it to do. So that's one of the things that's surprising, is that every once in a while, and Clippy calls you at least out when you have like very misshaped enum variants, where like A and B are tiny, and then C is like the entire world. But it's too easy in many ways to accidentally do this, and because box is an extra syntax element that you have to do, and maybe not even the right one to do at all times, fixing this later is a little bit harder. Not in all cases can you do something like Rust Analyzer to like refactor this automatically with like VS Code or something. This is another kind of thing. This is not directly related to Rust, but this is sort of the pre-story to this. There's a blog post from a couple of years ago about Schlemiel the painter's algorithms, which are the story goes, there's a painter. He paints the white lines in the middle of the road. On the first day, he makes 150 meters of white stripes into the road and gets paid 3 shekels for it. On the next day, he only has 75. And the owner of the company is already kind of confused, like how did you make so much less progress on the second day? But he's okay with it because still acceptable performance. On the third day, he makes 30 meters. He asked, like, what's going on? Why are you getting so much worse? And like, I can't help myself. The distance to the bucket is increasing. And C strings are this classical example, because in order to calculate the length of the string, you have to walk every single character until you find the 0 byte, and now you know how long the string is. And so if you keep using string cat to append to the string, every further attachment that you make to the string requires you to walk through the entire string. Classic other example is if you don't have an optimal index to go over via database, if you want to go through the entire database and you do it with offset and limit, so offset 100, offset 200, offset 300, you basically start at the beginning all the time. Why do we have this problem in Rust? We really shouldn't, because strings have lengths, and like this seems to be not a pattern that should happen in Rust. But it kind of comes up in two versions. One is sometimes we're afraid of lookups, of lifetimes. So rather than using an iterator of something, we tend to, for whatever reason, for instance, spawn a future with the index into something, and then the future by itself picks it out of a store somewhere, because we don't want to pass the lifetime into the future. And in that case, we keep having like the cost of plucking this item out of the container rather than having like the O of n to iterating through the container once. The other one is you can accidentally forget how expensive it is to clone a string. This is my favorite example, but we had this in so many ways already over the years. But this is just so funny, because when we fixed it, it was like a 100,000 time performance improvement for the for the bad case. So there's a source map. A source map consists of n tokens. We wanted to apply an offset to every one of those tokens. So you iterate over, let's say, 1,000 tokens, and you just move the index and column. But it also reassigns the reference to the source string. So you can imagine a source map is a piece of JSON that you basically say, like, at this location in the transpiled code are we in the original code? And by the way, what was that original source code? So if you have a 50 kilobyte original JavaScript file, then there is somewhere in the source map there's 50 kilobytes of the original JavaScript file in addition to the mapping. And what we were accidentally doing is that for every one of those tokens, we were kind of reassigning the original source string, which also meant that we were copy-pasting 50 kilobytes of string for every token. So the test didn't show this because computers are fast, and like the test fixture was 5 kilobytes, but then in production, people had 50 megabyte JavaScript files, and so it would grow. It's like in the previous version, it was running in 5 seconds. Now it takes 10 minutes. And in retrospective, it's very obvious to see, but if you actually write the same code in Python, you wouldn't notice it much, because you just reassign one string reference to another string reference, right? It's just, it's a O of one reassignment, because you don't actually clone every single byte. And strings in Rust are sort of a foot gun in some ways, because you don't necessarily at all times know who owns the string. And most of the time, you don't actually manipulate strings. So the string type in Rust really has two properties. It's a string builder, so you can append more stuff to it, which makes sense. But then it's also the thing that we use to store the final string that we have attached somewhere in a struct. And now it carries this extra capacity around just so that it can append at a later point. Whereas in a lot of cases, what you actually want to know is I want to pass this string to a bunch of other people too that might never manipulate the string, but because of lifetime issues, I also don't want to give it the borrow to the string slice. So instead of this, I should, in some cases, actually use an arg stir. And it's kind of well hidden that this is a string type in a standard library or an RC stir, and not a lot of people are using it, but maybe it should be a little bit more popular. Particularly with, and a lot of this is sort of inspired a little bit by not necessarily shortcomings, but the way we write async code is that quite commonly, you invoke a function which then returns a future, and that should do something with the string. So as a part of the API, you pass the whole string into it, and it does something with the string. But not all of those strings are transferring ownership from this first thing into that future. So imagine, for instance, you have a WebSocket connection or any other socket, and you want to send through this WebSocket connection a pre-serialized packet. If there's only one WebSocket, you can pass the vec u8 into that socket, and it does whatever it needs to send this buffer out, right? But what if you want to broadcast it to every member in the channel? All of a sudden, the most common way to do it in Python actually turns out to be in all of the APIs that I'm aware of for WebSockets in Python, in Rust, sorry, is to clone that vector for every member. Whereas we could instead have made it more popular to pass an RC of U8 slice, not slice. Well, I don't actually know what you call this. But this is not so popular, which doesn't make sense because like you cannot really make it into an RC at all times without incurring cost itself. But they're not super optimal. They're not bad. They're like good types, but it's kind of easy to make some mistakes. And they're kind of well hidden. Things that I wish we would have that are not major issues, but it would make our life easier. There was a time at Sentry when every error had a stack trace, and it was glorious. We used failure. And then failure sort of dwindled. And everybody replaced it with other things that are based on a fixed version of STD error. But alongside, we lost back traces, which now is a worse development experience than we had before. I know that anyhow has stack traces on it, but a lot of the errors that you would get nowadays from crates just don't really tell you where they're coming from, which can make it relatively tricky to debug. Also, errors don't really have names. So this is very specific to Sentry, but we report our errors into our own product, so we can dog food this. And so I would like to know, what's the name of you little error? And the only way for me to do this is I format the whole thing with debug and then parse to the first parentheses, which is just not clever. But in the absence of this, I can't really tell you like what's this error versus the other error, because yes, you can use std type name to some degree, but then when it goes through a wrapper, that sort of points at like a generic anyhow error at times. So that's a little bit suboptimal. There could be some improvement. This is a personal pet peeve of mine. I would like to have a new conversation of life before main / some sort of registry. There are a lot of things in the Rust ecosystem that use CTOR, which is, we should not talk about it because it does things that you shouldn't be doing. It basically registers static constructor from C++ land in Rust to register a function that does something once. But it's really, really useful because there are certain things that you want to do once on startup that are very innocent. Just register something somewhere. Imagine a test runner that wants to find all the test functions. If I want to have my own version of this, today I can't really do it. I can't like annotate something with an attribute and say like register this and then run this function. It would be nice to have this. And we kind of have a version of this in the community, but we don't really have it blessed. And for good reasons, because there are a lot of issues with it. But haven't found a good solution yet. Last part is specifically about async in Tokyo. I would say that the majority of our crates outside of like the core part of the utility aspect of driving the system is based on Tokyo. When we started, we use Actix, Actix Webs with the Actix Actor framework. And it felt good. It was good. Nothing wrong with it. But what turned out to be really challenging is to manage back pressure. If you're not familiar with an actor system, or specifically, I don't actually know if it's true for all actor systems, but it was definitely true for Actix. Every actor had a mailbox. The mailbox is basically it's a bounded queue where you can throw items into it, and then the actor would pick up the message that should process and do something with it. The problem is we basically had to set all of our queues to effectively unlimited size, because when the queue was full on the individual actor, you could sort of run into all kinds of issues. And it made it very unobvious how to do back pressure management. So it was very easy to like accidentally flood too many things into the system, and it would grind to a halt because it picked up too much work to do. So it eventually saturated CPU and just didn't want to do anymore. So when I don't even know if we got rid of all the pre-Tokyo 1.0 code at this point. Probably did, but in the act of moving from this world into a newer world, most of or all of Actix actually at this point is gone, and it was replaced with a lot more just raw Tokyo. And at that point, sort of my intrinsic knowledge of actually being in that code is also no longer there. But I talked to some folks. And at least for me, the guidance now is less async to some degree. Like not everything has to be async, but channels are not that bad. Like you can shoot many more problems with many more channels. There's a lot of one-shot channels going around at Sentry. There's a lot more explicit back pressure management through like there's a thing in the beginning that sort of controls how much can go into it, and then from there it goes into like a crazy world of channels. But it's not a bad pattern at all, and it solves a lot of the other problems that you run into that makes async I/O feel uncomfortable in Rust. So if you go with this idea, like you just spawn something and then out of that you talk of channels to the rest of the system, it actually feels pretty good. I think a lot of people that get very bad experience with async I/O or Tokyo or anything like this in Rust are, in quotes, holding it wrong. I was holding it wrong. I think this is a decent pattern to feel pretty confident about it. The risk of this is cancellations of futures in Rust are purely based on drop. And if you do something that is blocking on a thread or something of that nature, you can accidentally not cancel, and then you have a bunch of stuff still doing work that you didn't want to do work to begin with. This is also tricky if you do something like Tokyo select. The individual bits and pieces that are in the select block actually have to be cancelable, otherwise you can, or I don't know if it's true with select, but it's true with select all, for instance, that multiple things can be ready and they have to be cancelable. Or I think, I don't know what the property is called there. But this is not a Rust unique problem. My most frustrating programming experience this last year was for a Hack Week project I was doing Python async I/O, which is also not without faults. And it also has a cancellation problem. They have structured concurrency with a thing called the task group. And when one of the futures in there failed, it would cancel all the other futures, except a lot of code was written without cancellation in mind. And in fact, there's a ton of stuff in Python that's uncancelable. And it wouldn't even print you the error because it was waiting forever for all the other ones to cancel, except they were uncancelable. So it was the worst developing experience, because the only way you would ever get your error is to Control-C the thing out, and then all of a sudden you get all the errors. So cancellations are still hard, and maybe like cancellation token stuff like this should be sort of investigated a little bit. But yeah, there's something still to learn. Last part, I think Rust was really good for us. I would do it again. I think it's a really good language, and in some sense, I feel like there's a little bit of dissatisfaction in community at this point about how Rust is doing. There's some sort of negativity. So I want to give you some parting thoughts. I think a lot of people are really trying their best to build something, and they're maybe failing along the way. That might be true for the Rust Foundation, might be true for people in the Rust project, it might be true for community members. Because Rust made it very far, and building things like this is really hard. Even with the best intentions, you can still make some faults, some mistakes along the way. And maybe what we need is to talk a little bit better together to try to figure out how to move the language forward, how to solve some of the issues that we're having. There's a lot of things that can go wrong if most of the discourse is just happening online, particularly in social media. So things like EuroRust or other Rust conferences are a very good way to get in touch with each other and try to figure out how to solve some of the larger problems, because we can stand eye to eye together and figure out how to make this work better. Thank you.